Welcome guys. We're going to be looking at the concept of circular motion today. So this is an introductory video. The first thing I'm going to show you is a little snippet from Paul Hewitt on centripetal force. So watch and enjoy, and we'll go through some theory in a second.
I got here some water. I got some water here, gang. I got the water in the bucket. You guys know what I'm going to be doing with this water in the bucket? Because we're talking about centrifugal force, aren't we, right? I'm going to take this water in the bucket. What am I going to do? You go right over my head, and when I get the head top, I'm going to stop, right? No, I ain't going to stop, okay? Not if I can help it. Just go. Okay, maybe towards you guys, huh? Okay. You have confidence in the laws of physics, huh? Okay. But this is water, gang. Okay. How come the water didn't fall out? How many say, well, there's probably no reason for that. It's just that when it's spinning, the laws of physics break down. How come the water didn't fall out? Why? I take the ball and the string, and I swing the ball around and around and around. Or I swing it around like this. Okay? Or like that. How come the ball goes in a circular path? Maybe because something is pulling the ball out. That's what the little kids say. But you guys say, wait a minute, there's nothing pulling the ball out. Which way is that ball being pulled, gang? In or out? Begin with an I. Now try it. Okay. That's being pulled in. You know, a lot of people don't know that. They think that something's pulling the ball out. They think that when I whirl the water around and around and around, that something's pulling the water out. And they have a name for that. You know what they call that? They call it centrifugal force. Center fleeing force, a force going away from the center. But guess what, gang? There is no centrifugal force pulling outward on this ball, and there was no centrifugal force pulling outward on that water. The forces that acted on both these things was pulled which way? Inward. I have to pull on that string. If I stop pulling and let go, what's going to happen? The ball going to go out or just continue going? And this is the law of inertia.
Alright, so looking at Paul Hewitt video, I think it's quite a good one in terms of setting you up with what you need to do in terms of looking at the concept centripetal force. Right, so this is little proof that I'm going to show you, which I think is essential to be able to do. This is one that often gets asked in an exam. Right, so if we're looking at an object, let's say we've got a big blob of something with a string. Maybe it's a weight, which we'll do as an experiment. So if we're looking at this scenario here, and then the blob's going to go to a position there, and it will have also a velocity. Terrible drawing, but you can see that's going to be the direction. So the direction that the blob's going to be going at any time is always going to be at a tangent to the radius. Alright, so that's what I want you to sort of understand there. We would say the initial velocity over here is V0, or you could call it U, and this one over here is going to be V, that's going to be the final velocity. Now, there is a little formula for change in velocity. Now, change in velocity is equal to the final velocity take away the initial velocity. I'll get rid of that little thing there, sorry. Alright, so the final velocity take away the initial velocity. Alright, so if we consider that idea, then what we've got here is we've got our final velocity going that way, and we've got to take our initial velocity. Now our initial velocity is going there, So taking away our initial velocity means that there will be a vector going in that direction there. Alright, so if I do that, put my vector going there, that's my initial velocity, then what you'll see is that change in velocity over here is in fact directed towards the centre of the circle. Alright, so, and that is the centripetal force that we're actually looking at. So the centripetal force is always directed towards the centre of rotation. And that's a key concept that you guys need to make sure that you understand about circular motion. Now, anything that's going around, whether it be a satellite, whether it be a little weight put on a string, right, there has to be some sort of centripetal force acting there. Right, just moving ahead from there, I'll just come down the page a little bit. Right, so if we know that the change in velocity is equal to the final velocity take away the initial velocity, we're doing that as a vector calculation. Right, so that's a vector addition there. Now, if we were going to look at the force, right, so force is equal to mass times by acceleration. Right, so if we're talking about our centripetal force, it's equal to the mass times by the centripetal acceleration. Now, centripetal acceleration is equal to v squared over r. Alright, so that is on your formula sheet. Alright, so the next thing that we need to look at there is obviously putting that into there. So force centripetal is equal to mv squared on r. Alright, so that's the main formula that you'd probably need to work from. And again, as I said, the information for that is on your formula sheet. So another obviously thing that we'll be looking at will be a experiment where we're going to be looking at the rotation of objects. Now, one of the things is we know that v, the velocity, is the distance travelled over the time, isn't it? Now, if we're thinking of a circle, the radius of a circle is 2 pi r, and the time to get around that's called t, the period. So if you square that, you have to square the top line, so that'll be 4 pi squared r squared all over t squared. Right, so if I can put that into the formula over here, the force centripetal is equal to m 4 pi squared r squared, and that's all over r, and then t squared. So then I could cancel out that r with that r over there. So therefore my final formula would be m 4 pi r all over t squared. Now, when we do experiments, as we do in this particular one, what we will be doing is keeping some things the same. So in this experiment, we're going to keep r, the radius, constant. We're going to keep the mass constant. And what will probably happen from that is t, the period, will change depending on how much mass is on there. So what we could say is a proportionality between the force and t squared, the period squared. Obviously 4 pi squared, sorry, there should be a squared there. The 4 pi squared is always going to be a constant value. Anyway, we'll talk about this formula, this experiment, this investigation when we get to it in class. But that's essentially the relationship that we're looking at. So we'd say that the force is inversely proportional to the period squared.